Hello.
Good evening, sir.
Yeah, good evening. Okay, so you wanted to discuss diffraction, right?
Yes, sir, and the Young's double slit experiment as well.
Okay, so we'll do diffraction first. Uh, Young's double slit experiment is a problem for you.
Yeah, like I have read the theory, but then I keep getting confused in the numericals about the fringes and how to determine the bright fringes.
Hmm. Okay, we will. It will take 2 3 classes. We'll do everything. So we'll do diffraction first today, and then we'll go ahead with the YDSA after that. This part of the theory is not difficult actually, like in the sense that any question based on this will not be like something that you cannot solve. It is not going to be super tough. It is based on formulas. Once you understand how things come, then it should be easy. Okay. So we'll discuss diffraction. So first of all, you know what diffraction is?
Yeah, and the
Hmm.
wave of light is obstructed by an
Hmm.
obstacle. The light bends around the corners.
Hmm. So basically, the difference between diffraction and normal behavior of light is that, let's say we have a situation like this, and this is a gap, this is an opening, and light is coming like this. Now, depending on the width of this opening, if this opening is very wide, right,
Yeah,
compared to the wavelength of the light. So you have to compare the width of the opening with the wavelength. So if B is greater than wavelength, right? Then what happens is there are a lot of secondary sources that are created here, right?
yeah,
Like these are all wave fronts that are passing, and a lot of secondary sources are created, and they create, this becomes the next wave front that goes ahead, right?
yeah,
So finally, if there are many secondary sources here and it is like this, then you will get simple rectilinear propagation of light. You will not have any of the, you'll have a little bit, but little bit of bending, but not much. Most of the light will look like, if you observe on a screen, it will look like this portion will be eliminated and everywhere else will be very little light. Because the wavefront here, there are so many wavefronts parallel that it looks like almost parallel lines of light going ahead. Okay.
yeah,
However, if the situation is different in such a way that the slit width is not big, the slit width is small, right, compared to the wavelength of light, or basically B is comparable to lambda, right?
yeah,
Then there are only a few such wave fronts or secondary sources here, and if there are only few sources, then, or if there is only one source, let's say like this, then light will go in all possible directions like this from here. But if there are very few sources, the light will diverge. They are not parallel sources from where light, all of this light interferes to create a sort of parallel field, because there are many rays like this, right?
yeah,
If there are many sources like this, secondary sources, then it looks like parallel rays eventually. But if there is only few or one, then it will look like a spherical source of light, right?
yeah,
So finally, what happens is, if you observe this situation on the screen, it looks like light has bent. Light, there will be illumination here also and here also, even though the slit was only this thick, right?
yeah,
So this phenomena is called diffraction, where light is bending when it passes through an obstacle, but diffraction effects are visible only if wavelength of light is of the same order as the magnitude of the obstacle, or the size of that obstacle, or size of the hole, right?
yeah,
If the size of the obstacle is too big, then you will see rectilinear propagation of light and no diffraction effects. Okay.
Yeah.
So that is the first thing. Then the next thing that we have to understand is there are two kinds of diffraction. There is Fresnel and Fraunhofer kind of diffraction. So one of them is not in syllabus. So Fresnel is not in syllabus. We'll be dealing with only Fraunhofer diffraction. So the difference between this is just that this is Fresnel diffraction, where your source of light is at a finite distance, and then diffraction is also observed at a finite distance. Basically, this distance d1 and this distance d2 are both finite, right? So light will bend and there will be some diffraction. However, in this case, mathematically, it is difficult to analyze. Like the patterns here will be difficult to predict when everything is finite distances here. Okay. So this Fresnel diffraction is not covered in at least till the 12th standard level. So we will not be worrying about that. What is Fraunhofer diffraction? Fraunhofer diffraction is basically both these distances are supposed to be infinite. And what we mean by infinite distances, we mean that the rays of light should be like parallel rays of light should be coming. Parallel rays of light means the source is at infinite distance away, right?
Yeah.
And again, you will observe the interference pattern at an infinite distance. Now, that doesn't make a lot of sense because the light is diverging like this. So in reality, what people do is put a convex lens here, right?
Yeah.
So what happens then is that convex lens will take these rays and will make them parallel like this, right?
Yeah.
If you put a convex distance at the right appropriate convex lens at the appropriate distance from here, then it will make these rays parallel. No?
Yeah.
So then the screen can be placed anywhere and it will be as if this whole distance is infinite, right?
Yeah.
Similarly, actually, you're not putting the source at an infinite distance. The source is at a finite distance only, but you put a convex lens at the focal point, right?
Yeah.
So any rays that come from a source placed at the focal point of the convex lens here will come like parallel rays, right?
Yeah.
So both the source side and the detector side, if you use convex lenses, you can get the situation where we analyze and we call that as Fraunhofer diffraction. And that kind of diffraction is possible to analyze at this level, and that is what you have to study. Okay.
Yeah.
And this Fraunhofer diffraction, we will be studying in two cases. Fraunhofer diffraction in two cases. One is diffraction of light by a single slit, and the other is diffraction of light by a circular aperture. So single slit means the case that we have been talking about so far. Light is coming like this, parallel rays are coming, and this is the obstacle. And then again at the screen, you want to figure out what the pattern will be, right?
Yeah.
And again, these rays are supposed to come out parallel, obviously by placing a convex lens. So this is your single slit diffraction, about which you will have one or two formulas, a few results that you need to understand. So what we will be focusing on is the single slit diffraction now. Here, this width is B. And what we want to understand is at a particular point here, right? Or at a particular point here on the screen, what is the intensity, right? Because we want to understand how come there are bright and dark patterns on the screen, right?
Yeah.
Where is the maxima, where is the minima, what is happening? So we want to be able to predict what is the intensity at any point on the screen, right?
Yeah.
So the way people measure that intensity in terms of its position with respect to the obstacle is by talking about its angle, like this angle theta, right? So from the obstacle to the screen at any point here, you can make an angle theta and you can say intensity is a function of theta. We want to figure out this function, right?
Yeah.
At different points, what is the intensity, right?
Yeah.
So now if you think about the previous diagram only, but in a slightly magnified way, like we are just magnifying the previous diagram. We are saying this is the slit width. We are looking at it in detail, and parallel rays of light are coming like this. And there might be multiple sources here, right?
Yeah.
Right? There will be multiple secondary sources, right?
Yeah.
And what we want to do is find out the intensity at this point I of theta, right?
Yeah.
Where from the central point, this angle is theta, right?
Yeah.
So ultimately, what you want to do is figure out, due to all of these sources, right? What is the overall intensity at that point? Correct?
Yeah.
Like each portion acts like a secondary source. So due to all of these sources, what is the overall intensity at this theta point, right?
Yeah.
And the way you do overall intensity or overall amplitude whenever you have waves is you apply the principle of superposition, where overall amplitude or intensity will be due to the superposition of each of these secondary waves, right?
Yeah.
Okay, so that is the idea here. Now comes the mathematical analysis part of it. So what we can say is, let's say there are n secondary sources here, right? Like there are n secondary sources, correct?
Yeah.
If there are n secondary sources, we can number them like 1, 2, 3 till n, right?
Yeah.
And the total width is b, right?
Yeah.
So from 1 to n, the distance between each source, right? Distance between each adjacent source, we can call that as d. So you will get the equation that if there are n numbered sources, then you will say that n minus 1 into d should be equal to b, right?
Yeah.
Correct.
Yeah.
And in case n is tending to infinity, because obviously like this wavelength of light might be small, number of points could be infinity here, right? So
Yeah.
you can roughly say that n minus 1 d is equal to b equation is similar as n d is equal to b, right?
Yeah.
Doesn't make a difference n minus 1 or n, because n is going to be quite large, right?
Yeah.
So what we need to understand is, due to each of these n sources, what is the y1, y2, what are the displacements, right? Like actually these are all electromagnetic waves, so it's not technically a displacement, it's technically a change in the value of electric and magnetic fields, right? But the way you write waves is a sine kx minus omega t, right? Normal waves, right?
Yeah.
Correct. So
Yeah.
what we are saying is, in this case it will be actually E is equal to E naught sine kr minus omega t, something like that, right?
Yeah.
Electric and magnetic fields are actually changing. So, however, we will not worry about that. We still have to add similar types of functions, right? Y1, Y2, Y3, where Y1 and all stands for electric fields, right?
Yeah.
So ultimately, what you have to figure out is, when you add all of these sources, what happens to the overall intensity. So to know that, you need to know the actual phase difference between each of those sources, right?
Yeah.
When you do superposition of waves, when you do y1 plus y2, you need to know what is the, if this is kx minus omega t, what is plus phi, what is the next one, right?
Yeah.
Y2 will be a sine kx minus omega t plus phi, right?
Yeah.
So when you add that plus phi counts, because then only you'll get resultant amplitude correctly, right?
Yeah.
So we need to analyze that part now. So another, like, more magnified version of the same figure. So if you see, let's say we have a source here at the top and another source here. This is another source, this is another source. This is 1, this is 2, this is 3, right?
Yeah.
And each of these distances is d. We said the distance between adjacent sources is d, right?
Yeah.
So, okay. And we are interested in phase difference between these waves, which are going towards the same point, right?
Yeah.
So phase difference is related to path difference between the waves, correct?
Yeah.
So if this wave travels a bigger distance, then its phase should be bigger, right?
Yeah.
So we can, if we measure this gap, right? This gap in path, right?
Yeah.
That this gap is what matters, right?
Yeah.
So if my angle general, all of these are parallel lines. So angle is theta here, and this is D, this is D. So this will be D sine theta, right?
Yeah.
D sine theta, this path difference, right?
Yeah.
So the phase difference or length path difference between 1 and 2 is D sine theta. And if you see path difference between 1 and 3 would be 2D sine theta, right?
Yeah.
Because this will be 2D, right?
Yeah.
And if we know path difference, then we can get phase difference between 1 and 2 would be 2 pi by lambda into d sine theta, right?
Yeah.
Basically, d sine theta by lambda is unitary method, right? And then multiplied by 2 pi.
Yeah.
Makes sense?
Yeah.
And phase difference between 1 and 3 would be 2 pi by lambda into 2d sine theta, right?
Yeah.
So if you call this as phi, you will see that this is 2 phi, right?
Yeah.
And phase difference between similarly 1 and 4 would have been 3 5. Correct? Because it
Yeah.
would be 3d sine theta. No?
Yeah.
So basically what we are getting is that the waves will be such that, okay, if y1 was a sine kx minus omega t, y2 would have been same thing plus phi, and this would have been plus 2 phi, and so on, right?
Yeah.
Like this, these are the different waves going at that theta position, correct?
Yeah.
So your y resultant would be the sum of all of these, right?
Yeah.
Correct.
Yeah.
And if you do that sum, it is like adding a sequence of sines with all the angles are in AP, right?
Yeah.
Adding a sequence of sines, everything is having same amplitude because ultimately these were part of the same wavefront from the source side. It was part of the same wavefront. So you will assume that they are being split like this, AAA, all of them are AAA, right?
Yeah.
And when you add a sequence of sines, there is a formula, if you remember. Sine, suppose you have like this, sine A, sine A plus D, and so on, right? Sine A plus n minus 1 into D, right?
Yeah.
When you add a sequence of sines where angles are in AP, there is a formula which says it is going to be sine n common difference by 2, n time the number of terms into common difference by 2 by sine common difference by 2, and then sine first plus last by 2, right?
Yeah.
Do you know about this trigonometric result?
Right. Some of terms of AP, it's like a similar formula, right?
What?
Like we have some sum of AP, how we take it.
This is a result that is there in SL Loni, and it will be there in your Allen book also somewhere in a formula. Okay.
Yeah.
Like you have seen this before, no? This thing.
Yeah.
Similarly, if it was a cos series, right? Everything would be same. This term remains same except this becomes cos.
Yeah.
Okay.
Yeah.
So this is a standard result. So if you apply that to this situation, what happens is your y resultant comes out to be something like this: a sine n phi by 2 by sine phi by 2 and some sine. This part is not so relevant. This is the wave part, omega t minus kx and all, right?
Yeah.
Why is this part not so relevant? Because we are concerned with this amplitude, okay? We are concerned about the amplitude because that will give us the intensity, right?
Yeah.
This is the wave part of that function, right? So what we get ultimately from this is that resultant amplitude is equal to a sine n phi by 2 by sine phi by 2, right? And here phi was what? Phi was equal to 2 pi by lambda into d sine theta, right?
Yeah.
What we had seen earlier.
Yeah.
Okay, so this is the resultant amplitude of the wave. This is your first equation. You should write that down, these two results. Then if resultant amplitude is this, then intensity I of theta would be some k times your amplitude square, right?
Yeah.
Intensity is some constant and is proportional to amplitude square, right? So intensity I theta comes out to be k times, you have a square sine square n phi by 2 by sine square phi by 2, right?
Yeah.
Okay, so if you multiply the top part by n square and n square, denominator also by n square, right?
Yeah.
And then you get on top, you get I of theta is k a square n square sine square n phi by 2 divided by, here you can write, since this theta will be small because infinite separate very far away you are saying, and the slit width is small and all, so you can say sine 5 by 2 is similar to 5 by 2, so you can write this as phi square by 4 n square, right? Correct.
Yeah.
Or basically you can write this as n phi by 2 whole square, right?
Yeah.
In the denominator.
Yeah.
Okay, so I will just write that separately here. I of theta is coming out to be k and na whole square na sine n phi by 2 by n phi by 2 whole square. I'm just simplifying it and writing it like this, right?
Yeah.
Now think about it. Now secondary sources, this was one wavefront that came like this, right? And then many secondary sources were here, right? Correct.
Yeah.
So if your initial amplitude is a naught, this was the amplitude of the incident light, right?
Yeah.
Then the amplitude of the wave will be equally divided between all these sources, right?
Yeah.
Because your total energy has to be same, whatever came has to go, right?
Yeah.
So you can say that if you're calling each of these waves having amplitude a and all, right, the a naught should be equal to n times a, right?
Yeah.
Because when we were doing the interference, we were saying this wave was a sine something, this wave was a sine something, so this a naught should have been n times a, right? So your initial light intensity I naught would be k a naught square would be k a square n square, right?
Yeah.
This is I naught that came to the slit, right?
Yeah.
So if that is k a square n square, now you can see that there is a k a square n square here, right?
Yeah.
Right. So you can say I of theta would be equal to I naught, right? I naught can be taken out and you can write sine square n phi by 2 by n phi by 2, right? Whole square, right?
Yeah.
Correct.
Yeah.
Now let's call beta as n phi by 2, right? Beta is n phi by 2, where that means beta becomes n by 2 into what was phi? 2 pi by lambda d sine theta, right?
Yeah.
So this becomes n pi d sine theta by lambda. Beta is this. We are calling a new variable. That gives us the formula that is written in most books. That is I naught into sine square beta by beta square, right?
Yeah.
This is your result for intensity at a theta location, angular position of theta due to diffraction by a single slit, right?
Yeah.
Here again, beta was what? N pi d sine theta by lambda, right? And
Yeah.
if you remember, we had written b is equal to nd.
Yeah.
So we can write nd as b. So beta can be written as pi small b sine theta by lambda, right?
Yeah.
So now these two results are crucial for you because here we get the beta angle in terms of the slit width and the angular position and wavelength. And then from beta, we can find out what is the intensity at theta, right? Correct.
Yeah.
So again, these two results are important for you to remember. You should write them down and see how it has come, right? It is
Yeah.
just a consequence of doing your normal interference due to n different wavelets, right?
Yeah.
Okay. So now what we need to understand is what are the implications of this. So these two formulas, right? So what are the implications from this? So first of all, you have to realize at theta is equal to 0. That means what is the position? The position is at the center here when theta is 0, right? Correct.
Yeah.
Your beta becomes what? Beta is also 0 because beta was pi b sine theta by lambda, right?
Yeah.
So beta is 0 and intensity I is equal to I naught sine square beta by beta square, right? Correct.
Yeah.
Now beta is tending to 0, so this limit tends to 1, right?
Yeah.
So this is I naught, right?
Yeah.
So at this point, you get I naught intensity, which was what was the initial intensity of light, right? Correct.
Yeah.
Are you understanding why this is maxima here?
Yeah.
The central diffraction maximum, right?
Yeah.
Okay. Now, what happens when beta is equal to m pi, right? Some multiple of pi, right? So then what we'll have is sine beta would tend to 0, right?
Yeah.
So I of such theta would be 0, right?
Yeah.
So theta at those theta where beta is m pi, right? You will get 0 intensity, right? So minimum, right?
Yeah.
So when is beta going to be m pi? M pi is equal to, you'll put beta expression like this. You say pi b sine theta by lambda, right?
Yeah.
So this cancels and you get the result that whenever your b sine theta is equal to m times lambda, right?
Yeah.
You get minima, right?
Yeah.
So notice that this is a little counterintuitive because normally earlier you used to have like whenever it was integer multiple of wavelength, it used to be maxima, right? In interference.
Yeah.
But here the intensity expression is such that at these values of beta, your intensity is becoming 0, right?
Yeah.
So when b sine theta is equal to m lambda, here theta stands for this angle. At any position where b sine theta is equal to m lambda, you get a minima, right?
Yeah.
Makes sense.
Yeah.
So again, this result is important to understand this, why it is a minima here and when the minima happens, right? So
Yeah.
if you put m is equal to 1, 2, 3, you get different angles at which minima will come, right?
Yeah.
Different angles theta for minimum intensity, right?
Yeah.
So when is the first minimum going to happen? When m is equal to 1, right?
Yeah.
So therefore, the angle at which first minimum happens is sine theta 1 is equal to lambda by b, right?
Yeah.
So that will happen when theta 1 is equal to sine inverse lambda by b, right?
Yeah.
Correct. This will
Yeah.
happen on both sides. So both sides, there will be an angle theta 1 at which the first minimum will happen. This is first minimum. And this is also first minimum, right?
Yeah.
At both sides, theta 1 separation, you will get first minimum, right? So
Yeah.
the total angular width of central diffraction maxima. So diffraction maxima. If you see the screen, you have a central maxima here, central maxima, right? And
Yeah.
you have one minima here, first time, and one minima here at equal angles, right? Correct.
Yeah.
So technically you can say that the maxima has this much width. After that, the first dark point is there, right?
Yeah.
So total angular width of the central diffraction maxima can be said to be 2 times theta 1, right?
Yeah.
So that is 2 sine inverse lambda by b, right?
Yeah.
Okay. Now, what are the other points? What are the other points? Other points you can obviously find by putting 2 and stuff, right? In b sine theta is equal to m lambda, right?
Yeah.
You'll get different angle. Sine theta 2 will be m lambda 2 or 2 lambda, right?
Yeah.
Sine theta 2 would be equal to 2 lambda by b, right? So we'll
Yeah.
get another point probably somewhere here and somewhere here and so on, right?
Yeah.
Second minima, third minima, and so on, correct?
Yeah.
Now, what about maxima, however? Like obviously, if you have first minima here and second minima here, then some point there should be a maxima between this minima and this minima, right?
Yeah.
If this is a minimum in intensity, then it must have risen, right, to get a second minimum here.
Yeah.
So what about maxima? So how do you find maximum points where intensity is maximum? To do that, we will take the intensity expression. The intensity expression was what? I theta was I naught sine square beta by beta square, right?
Yeah.
And beta was basically pi b sine theta by lambda, right?
Yeah.
And what we will do is we will do di by d of beta, right? Like we want maxima of beta, right? Maxima of intensity, right? So
Yeah.
we are differentiating the intensity expression with respect to this beta variable and saying di by d beta should be 0, right?
Yeah.
So when you do that differentiation, you will get something like this: beta square beta sine beta cos beta minus sine beta into 2 beta by beta power 4 is 0. right?
Yeah.
And this will simplify, and you have to say numerator should be 0 for it to be 0. So you will cancel one beta, beta square will be left, and you will cancel sine beta also. One second, let me check if I'm doing it correctly. You will have 2 here, no? There will be a 2 sine beta cos beta. Beta square into 2 sine beta cos beta minus
Sine square beta, right?
sine square beta into 2 beta. Yeah, this is the expression, right?
Yeah.
And 2 cancels, beta cancels, and we have sine square beta is equal to beta sine beta cos beta, right?
Yeah.
And that gives us tan beta is equal to beta, right?
Yeah.
These are the points where maxima or minima could happen, right?
Yeah.
We already know, however, that minima positions are whenever beta was m pi, right?
Yeah.
We already know all the minima positions. So this equation is not satisfied by m pi. So these must be the maxima positions, right?
Yeah.
Now, one thing to realize here, slightly different, is that if you look at a tan graph, tan x graph, right? Tan x graph is repeating like this, correct?
Yeah.
It repeats like this and goes on like that in minus pi by 2 to pi by 2 and so on. So this equation is like solving tan x is equal to x, right?
Yeah.
If you draw your y is equal to x line, right? You will notice that there will be some intersection point here, then some intersection point here, then other intersection points will again be far off and all, right?
Yeah.
So one thing to notice is that there is no fixed gap between this and this, right?
Yeah.
Like every time there is an intersection of tan x and x, that is the point where maxima happens, right?
Yeah.
But according to the graph, like obviously this is a rough diagram. If you plot it yourself or using a computer, you will realize that these points will be found at not at the midpoint of minima. Like normally in a regular diffraction pattern, regular interference pattern, what happens is there is a central maxima, then there is minima, then another minima, and in the middle of two minimas, there is a maximum, right?
Yeah.
In YDSE, at least, that is what happens in YDSE. And anytime between two successive maxima, in the midpoint, there is a minimum, right?
Yeah.
But here you will see that your maxima is at these locations, right? So this is not going to fall exactly in the middle point of these points, right?
Yeah.
These are dependent on the solutions of this equation, correct?
Yeah.
So that is why there is no, in books and all, you will not see any formula for maxima, central, other maxima, right?
Yeah.
Like in the books, they just mention that minima is at b sin theta is m lambda, right?
Yeah.
They don't say anything about maxima because actually for maxima, you have to do this calculation and it happens at like slightly more weird points, right?
Yeah.
Okay, so that is your maxima, minima. Now we have found the angular width of the central pattern, right?
Yeah.
We said that that was 2 theta 1 or 2 sine inverse lambda by b, right? Of the
Yeah.
central maxima, the angular width was this much. Now, if someone says, okay, what is the actual distance on the screen between the central maxima, right?
Yeah.
Correct. So distance on the screen will be calculated on the basis of the fact that when you are doing this diffraction, you are placing a convex lens here, right?
Yeah.
so that different parallel waves that are coming can converge on some point on the screen, right?
Yeah.
Because otherwise it doesn't make any sense. No, you'll not have a screen at infinity distance, right? Because when we did the calculations, we assumed each wavelet was sending parallel lines, like then only we took phase difference like this. No,
Yeah.
these were all parallel rays when we did the calculation, right?
Yeah.
So, but actually screen will be at a finite point. Screen will be at some place here, right?
Yeah.
The way you collect all the waves on the screen is by putting a convex lens such that all parallel waves will be focused at the focal length distance, right? This distance should be focal length, right?
Yeah.
Then only all of these parallel waves will converge at a point here, right?
Yeah.
So this distance will be equal to the focal length of this lens, correct?
Yeah.
If that distance is equal to focal length and the angular separation we have already found out to be this much, right? Between one minima here and one minima on the other side, then f into that angular separation will give you the distance here, right?
Yeah.
You understand why you have to multiply by f?
Yeah.
Because on a circular arc, if you have theta separation, then f theta would be this distance, right? Correct.
Yeah.
So because the angles are anyway small, this and this are considered similar. And therefore, we say that actual separation on the screen would be 2f sine inverse lambda by b on the screen distance, where f stands for focal length of the convex lens here, right?
Yeah.
Are you understanding?
Yeah.
Obviously, this is just for the first minima. For second minima, it would have been 2 lambda by b and stuff, right? Everything would have been 2 or 3 and stuff, right?
Yeah.
So that is your overall diffraction by a single slit situation. Now, a few special cases. Case 1 is when beta is greater than lambda, right? Or when b is greater than lambda, then you will see that theta 1, b means the slit width, right?
Yeah.
And you will say theta 1 was what? It was sine inverse lambda by b, right?
Yeah.
So that tends to 0 now, right?
Yeah.
So basically that means that you get the diffraction minima is happening at the origin only, right?
Yeah.
So it's almost like the dark fringe will happen near the origin only. So it's like this point onwards there is darkness. Like the first dark fringe happens near the line here, right?
Yeah.
Basically this is just saying that in this case you will not see any diffraction pattern, because it will look like all light is just focused here and immediately after that there is darkness, right?
Yeah.
Like normally the darkness was at a wide place, right? First time it was dark.
Yeah.
That meant that okay, light has bent because this much area is illuminated, right?
Yeah.
But if the darkness starts here, then obviously that means that you are just passing light in rectilinear propagation, right?
Yeah.
So that is your case 1, which explains why your slit width should not be like this. Normal cases are when beta is similar to lambda. Then you see the cases that we already discussed, right?
Yeah.
And when beta is equal to lambda, if beta is equal to lambda, right, then you get theta 1 is pi by 2, right? Because it is sine inverse lambda by beta, right?
Yeah.
So theta 1 is pi by 2, which means the central maxima will spread on the whole screen. Why? Because the first time that there is a minima is at a pi by 2 angle, which means like minima is somewhere here, right? Pi by 2 angle.
Yeah.
So that means the whole screen is illuminated, right?
Yeah.
Although the intensity will decrease gradually.
Yeah.
Intensity decreases, but the whole screen is illuminated, right?
Yeah.
Okay. Similarly, in case you have beta is less than lambda, right? Correct.
Yeah.
Then theta 1 is not possible. No theta, no such value, right?
Yeah.
So that means that no minima is anywhere obtained, right? So
Yeah.
almost like uniform illumination will be there. Again, this shows us that no minima is obtained means nowhere on the screen is dark, right?
Yeah.
So again, light seems to have bent, right?
Yeah.
Like you are seeing diffraction because clearly then the whole screen has become illuminated, right?
Yeah.
Because no minimum, right?
Yeah.
So obviously, like how the intensity of light at any of these points will be low, but it will be lit. Like obviously initial energy coming in is distributed over a whole big screen here. So it's not like intensity will be great, but it will be lit, which means that light has bent, right?
Yeah.
Also, one point I forgot to mention was what happens. We knew that at central maxima, intensity was I naught. Maxima intensity was I naught, right? Correct.
Yeah.
What happens at other maxima? Other maxima will happen when what equation was satisfied? When tan beta was equal to beta, right?
Yeah.
And intensity would have been I naught sine square beta by beta square, right?
Yeah.
So if you use a calculator and try to see which are the angles at which this happens, right? Tan x is equal to x, right?
Yeah.
You'll get some solutions for this. There are infinite solutions actually. You'll get some solutions. Even if you take the first solution, right? And
Yeah.
put that value of beta in this expression, you will realize that the value of I that comes at the, let's say, first maxima, which is not central maxima or second maxima, you can call it, right?
Yeah.
The value of I that comes out is quite low. Like it comes out to be I naught by 21. Okay. So and the third maxima that happens, that comes out to be I naught by 59. Like these are obviously weird numbers because the angles will be weird here when this happens, right?
Yeah.
So after that, the calculations have been done and this is rough values. So it shows us that the pattern is like this, like the central maxima has this I naught intensity. And after that, minima will come and then some maxima will come and then some small maximas will come, right?
Yeah.
This maxima is only I naught by 21. This maxima is only I naught by 59. So it is sharply declining, the maximas. Okay.
Yeah.
You understand?
Yeah.
That is happening because this equation will give values and the I naught can be calculated from there. Obviously, the minimas will be zero intensity here and so on, right?
Yeah.
And you have to keep in mind that this is not, even though in the diagram that I have drawn right now, it looks symmetrical. These points don't have to be in the midpoints, right?
Yeah.
These between these two, it's not like this is in the midpoint, the maximum, right?
Yeah.
It happens when this happens. Correct?
Yeah.
Okay. So that is your diffraction by a single slit. The second kind of diffraction that you need to know is diffraction by a small circular aperture. Small circular aperture. So basically what you will have is a screen will be there like this, and there will be a small hole here. Okay. And light rays will be coming. And from here, light rays will be coming like this. And again, you will put a convex lens here, which will focus the light rays. And you will get a pattern on the screen somewhere here, right?
Yeah.
And what happens here is there are circular dark and bright patterns, fringes. Okay. There is a central disk. There is a central disk, which is a bright disk, central bright disk. And after that, there is a dark layer, dark disk, and then there will be a second bright disk and so on, right? Dark disks, and then second bright disks and so on. The analysis is similar to what we did for that, the single slit case, but this analysis is slightly more complicated and is not shown usually. What happens is you just have to remember the result, final result, and only two formulas you need to remember in this case. That what is the angular position of the first dark fringe. So again, similar to what we did earlier, this is the circular aperture, let's say. So what I want to figure out is what is the angular position, this angle theta, for the first time the dark strip comes, right? Right.
Yeah.
Are you understanding that it's similar to the previous case? In that case, it was angular position of the first dark spot, right?
Yeah.
That was your theta 1, right?
Yeah.
And this was your corresponding other side theta 1. Now the only thing difference is that this is a circular hole, so now circular discs will appear like that. Everything here is bright, okay? Central bright disk. After that, there is a dark disk for some portion, right?
Yeah.
And then there will be a bright portion, and then there will be another dark portion, and so on, right?
Yeah.
So your first dark position theta 1 here will be given by 1.22 lambda by d. Okay. Here, what is d? D is the diameter of this aperture. D is diameter of aperture. Okay.
Yeah.
So obviously, again, by same principles, you are observing it on a lens here by focusing it on a disc here by focusing these rays through a lens. So it has to be on a focal length here, f, right?
Yeah.
Basically, it is all Fraunhofer diffraction, where actually the screen should be placed at infinity. But since you have to put a convex lens to achieve that effect, you have focal distance of f here. So if you want radius of this, right? Radius will be f into theta 1, right?
Yeah.
So 1.22 lambda f by d is your expression for radius of this disk. This is radius of circular bright disk, central bright disk, right?
Yeah.
We keep in mind that the d here is the diameter of the aperture, not the radius of the aperture. This d is diameter, this is the radius, f into theta 1, right?
Yeah.
Correct.
Yeah.
Now, if you have a very large aperture here, then obviously you'll not observe any diffraction. You will just see rectilinear propagation. Okay. Same
Yeah.
as before. Correct.
Yeah.
However, like for this circular aperture stuff, these are the only two things that you need to remember. Other higher order bright fringes or dark fringes formulas are not necessary. You will mostly be concerned with the first dark fringe, right? And
Yeah.
what is the radius of that disk? So these are the results that you need to know. Beyond this point, nothing more is required. Mostly it will be about the main derivation that we did for the diffraction by a single slit. That derivation will be important, and the results that I mentioned there. What you can do is try out a few of the diffraction questions now. We can also do some examples in the next class. Some examples on diffraction we can do, and then we can do YDSC. Okay.
Okay.
So try out some diffraction questions. I will also discuss some examples with you. Once we are done with that, we'll do IDSC. Like in the next 2-3 classes, we should be able to finish this whole section.
Okay.
Next class will be tomorrow, and we'll continue from this point. We'll do
Okay.
daily classes for a few days to finish this off. Okay.
Yeah.
What is happening in your tests and all right now?
The Allen tests are going fine.
Hmm.
I started doing the NTA papers,
Hmm.
like the NTA app. So I just started doing that.
Hmm.
So it's like ranging between 190 to 210 as of now,
Out of 300,
out of 300.
the mains one.
The mains test, the full syllabus test. And I'm trying to do like at least 2 of them per day.
Okay, one thing to note is don't do 2 per day. Don't do 2 per day because it's a waste of your time. Like you have given many tests. Now it's not like you need to do familiarity of tests, right? Like you are already very familiar with tests. No.
Yeah.
So if you are doing them in time, don't do 2 per day. Don't even do 1 per day. You should do like 1 every 2 days. I
Okay.
mean, why? Because see, doing tests is not a problem now. The problem is about revision and memory. Revision, memory, making sure that every portion of the syllabus is covered. All of that is more important, right?
Yeah.
And if you see on the NTA website, there will be like I think hundreds of papers, right? How many papers are there?
There are 300 papers.
So there are 300 papers. You'll never be able to finish them in time. So reduce the number of actual timed tests. What you should be doing is going through the papers, not as if you are doing a test, but looking at the questions and seeing that I can do this, I can do this, I cannot do this, I should try it out, right?
Yeah.
So don't spend 3 hours every day doing so many tests. What you should be doing is like don't even do the questions if you know how to do it, right?
Yeah.
Don't do it. Go ahead. What you want to do is go through as many of these before your main exam, right?
Yeah.
So you need to go through them. Go through them even by reading the questions is enough if it is obvious to you that you know how to do it. Like what you need to discover is what are the portions that you don't know how to do, right?
Yeah.
So I recommend like spending that many hours just going through the questions. If you find any difficulty, solve it, see the solution, try to see it. If you are getting stuck, make it note of it and we can discuss them. But go through more questions and do one test every 2 or 3 days as practice for timed situation. Focus more on going through the questions and doing your revision because your score will improve from 210 to 230 if you like are fully revised and if you do a little bit of revision, right?
Yeah.
It is less and it used to be 240 and all no sometimes in our other tests, right?
Yeah.
So the reason it is slightly less is because some portions you might have forgotten or you're missing some stuff. So if you want to increase that, you need to go through the questions, not as a timed environment, just to check your knowledge and find out where you're lacking, what is missing. And do time tests every once in 2-3 days and all, but no need to do so many tests every day. You should try to get through as many papers as possible, right? And getting
Yeah.
through those papers will take time. Getting through those papers, even if you don't solve the papers fully, it might take 1 hour to go through the entire paper, right? There are 90 questions or 75 questions, right?
Yeah.
So even just looking at it, you might not do 40, 50 of them, but you might have to think about some. So it might take 2, 3 hours to just go through a paper, right?
Yeah.
So you don't have so much time. So don't waste your time in doing things that you already know. You understand?
Yeah.
More time should be spent on revision, recall, memory, finding gaps, fixing those gaps, and less time should be spent on doing things that you are already good at. Because those things you will not lose in any time. And enough test practice is anyway going on. Alan is doing tests, you are doing tests. No more tests are required, right?
Yeah.
Those doubts that you have sent, those are from what? NTA or Alan?
Those are from Alan.
Okay, so we'll discuss them. Once we are done with this theory of diffraction, YDSC and all, we'll do the doubts. Okay.
Yeah. So for revision, like, would it be better if I like quickly revise like 2-3 chapters a day by just going through the theory, or just reading through papers and then finding what I've forgotten?
Don't do 2, 3 chapters a day. Don't do revision by doing theory reading. Do revision by looking at the NTA questions. You understand?
Yeah,
If
just
you look,
going through the papers.
going through the actual NTA papers, you will find out which topics you need revision, right? Like if there is any doubt in something, that is how you will discover actual problems, right?
Yeah.
Don't spend time in reading a book now, because anyway you have done enough of that. Now just go through the questions, and through the questions you will realize, okay, I need to see this. Then you see that thing right then and there, right?
Yeah.
But don't do separate revision time. It's by looking through questions that you do revision.
Yeah.
So do that, and like if you can cover a lot of those NTA papers by just going through them and finding out what are the problems, then your preparation will be solid. Okay, because nothing beyond that is going to come in the actual exam. So you don't have to worry. Like if you go through 50 papers, it's not like anything new can come, right?
Yeah.
So when is your test? When is your exam?
JEE?
Means
It's supposed to be dates are from April 26th to May 2nd. So any date in that they would give.
yours is not yet come yet.
Yeah, it's not come yet.
Okay, fine. So enough time is there, and anyway your preparation is fine. So just in the next 10, 15, 20 days and all, like find out the problem areas so that we can do classes only about the problem areas, right?
Yeah.
Maths and physics, any areas that are coming as problems in NTA questions, you should find them out. We'll do classes as many as needed, right?
Yeah.
Okay, I'll see you tomorrow then.
Thank you.
Bye.